So you have, so if I look at the concept stage, if you follow the gray color, it can have a long tail. And you can keep coming back to it basically in all stages. That's why it is a long tail. Then the design stage, now see the hard starts and stops are for management's thinking, right? Because they need hard dates, otherwise they can't run the business, right? That's for engineers, it's a different cup of tea. The design stage may start earlier than management thinks, or earlier than what we document, because as soon as you have a concept stage, you may start schematics. You may start, now again, it depends on definition. Concept stage means you are validating the concept. Design stage, you begin to draw your schematics, right? You begin to think about component selection, right? So you may start design stage earlier than what you document as a start of design stage. Same thing happens in the prototype stage, same thing happens in the first articles, and same thing happens in the production, right? But for the sake of planning, you have some hard stops and hard starts. And now, on top of this, we're going to impose a role of simulation. Of course, simulation has been actively pursued in the concept stage and design stage, less so in the prototype, first articles, and production stage. So what I would like to suggest to you today is think about incorporating simulation in various stages, and then we're going to also impose statistics. Statistics means that now we are actually getting serious about getting data from the prototypes, from the first articles, from production, keeping in mind the principles of statistics. You do gather performance data for prototypes. Now I'm thinking about is, okay, if you're building few prototypes, let's say 10, they can be statistically significant. So think about gathering data in the prototype stage using statistical principles. And they're not very hard to follow. Okay? Any questions on this one? Okay. Here is what we have divided basically a circle, various stages in the circle. For a new product, you start with the concept stage, into design, and simulation essentially becomes increasingly complex, right? So we have a green strategy for the concept phase. So green simulation strategy for the concept phase, yellow strategy for the design phase, orange for prototype, Indian red for first articles, and production phase is red strategy. So the colors indicate increasing complexity. Now, this is sort of a circle because the assumption is that you are accumulating body of knowledge through integration of statistics and simulation. You are accumulating body of knowledge which will feed into your next product development cycle. That's why it's a circle. Of course, you don't want to be in this circle all your life. You want to finish your product and then shoot off. But your body of knowledge continues to grow, and as a result, you continue to develop better and better products. So in the green strategy, what are your simulation objectives? Some of the examples we have here is that you want to verify your concept. You want to verify idle circuit behavior. You want to verify performance, technical feasibility. Right? So those are the things which you want to verify in the concept phase. Choice of tools. You have got quite a few choice of tools available in the marketplace. MATLAB, Simulink, Spice, MathCAD, Simplore, Sabre, so on and so forth. Based on how deep your pocket is, you can invest a lot of money in tools. Rule of thumbs: concept clarity, And again here, I don't want to repeat, simplicity is important, idle components are important, right? You're really focused on validating the concept. Design phase strategy, the yellow strategy. We have a circuit behavior, performance validation, component selection. Those are some of the objectives. Again, choice of tools, SPICE, Implorer, Saber, etc. And then it gets more complex as you go through prototype phase. You have got and now you're also validating the process. The process validation requires statistical acquisition of data. And then you have first article strategy, where you take your statistical data and you again begin to evaluate manufacturability. It becomes more important. Evaluation of manufacturability is when you're developing a highly complex product. You have got motor drives is one example. You have got electromagnetic components. You have also got semiconductor components, and you may have some components which are basically, you have an array of components using different processes. And here, how are the processes distributed? And we'll talk about that in a minute, so that it becomes clear. So, manufacturability is your product feasible to manufacture, and are you able to collect that data and make it part of your simulation? And then production strategy is pretty similar to first article strategy. Nothing more to say here.
Can you explain a little more on the process validation? I'm not very clear. How will you validate the process of using the simulation tool?
Yes, yes. See, as a matter of fact, that's my next slide.
Sure.
Let me all right, let's get to that. Let's get to that. Now, in the whole body of knowledge of statistics, there is one particular curve which is most important for engineers, right? And that particular curve is the normal distribution, right? Now, normal distribution basically is a great way to understand the process, right? So when you collect data, and now, what is the theory behind normal distribution? Basically, it says that if you have random variables, right, and a tolerance on a component is a random variable, outcome of a process is random, right? It has a tolerance. Everything in engineering has a tolerance, right? So when you look at, when I have got 100 components and I measure their values, I'm able to develop a normal distribution, right? So process is the same way. And the processes are supposed to have. So, for example, if you have a process of, let's say, machining a back iron for a permanent magnet motor, right, or machining a cover, or die casting a body for a rotating component, then tolerances on that component depend upon the process being used in manufacturing it. And consequently, at least the theory says, that the tolerances are normally distributed. What does that mean? that means that majority of the component values. Good morning. And we have one seat here and one seat there. So when you look at the normal distribution curve, essentially this is your mean position. Now plus sigma standard deviation, minus sigma standard deviation and plus sigma standard, 68% of the population. Now there are two ways to predict this, okay? One is I can say 68% of a component tolerance population is within plus minus 1 sigma. Or I can also say that when I pick up a component, the probability of it having plus minus 1 sigma tolerance is 68%. Right? So both the interpretations are correct, right? So in engineering, whether you are looking at components, whether you're looking at processes, you have to think about that all the processes, all the components have a normal distribution. Now that gives you your frame of reference. That gives you that, okay, this is the frame of reference with which you are going to beginning to evaluate your manufacturing, your prototypes, and then that's how you begin to incorporate that data into simulation as well. And then I'm going to take it a step further. Now this is really about two things. One is you want to develop a product in a very short period of time, and when you are done with the product, it has to be a world-class product. Now you cannot develop a world-class product without paying careful attention to statistics. It's just not possible, right? Without knowledge, you can forget about developing a world-class product, right? And shortening the product development cycle is only possible when you have got the right tools with the right knowledge. Okay, and I'm going to take this a step further and say, how do you make sure you continue to develop world-class products? Okay, so we talked about component tolerances, right? So component tolerances, you think of component tolerance as a normal distribution, and you have got minus tolerance and plus tolerance. Now you also have some, let's say if you're using a mechanical part, you may have lopsided tolerances. You may have, say, minus 0 plus 1%. Even then, that tolerance is going to be normally distributed with left and right extreme. So you can always adjust your mu, which is the mean, and sigma, which is the standard deviation, with respect to your tolerance. Okay? The minute you incorporate statistics, things begin to change dramatically in terms of looking at your manufacturability. So this is something we talked about, that this one is plus 2 sigma minus 2 sigma, that probability of X having value in this range is 95%. And there's a curve later on where you'll be able to see different probability distributions, different values. Here it is. So when you have, so 68% of your population will lie in plus minus 1 sigma. Okay? And then with plus minus 2 sigma, you're almost at 95%. And with plus minus 6 sigma, you're at, I think, 99% or something like that. Right? So this is how your tolerances are. So if you have tolerance here, you can say, okay, 68% is going to be in that plus minus 1 sigma. Okay, now what really happens at the manufacturing level? What begins to happen? Right now, normally when you have an incoming inspection, when you order a part from outside, you have an incoming inspection, you will inspect mainly, you have one component or two components, you will inspect mainly that it is within tolerance. You don't care about anything else, right? You really say, okay, I have, take a simple example. I have a resistor, or I have an inductor, I have a transformer. Okay, my inductance value was plus minus 2%, 5%, right? So as long as your vendor is able to give you component within this range, you're happy, right? You may not know the probability distribution. The vendor may have enough money in his quotation that he is reworking these components which have fallen out of tolerance. But you're happy because you're getting within plus minus. But remember, when you're doing design, the basic assumption is that everything is normally distributed. Everything has got 68% of the population is in plus minus sigma, and it has implication because when you begin to simulate, simulation also assumes everything is normally distributed. Now things begin to skew, things begin to fall apart when you say, well, actually the majority of the components are lying in this range. Now what happens? Now I want you to think about bigger picture, patterns. I want you to think about, when you have a design, when you have a system, if everything is normally distributed, everything is random, output is also normally distributed. But when things are not normally distributed inside a system, then output is. So that's something you want to think about. There are two good numbers, and it's simple to incorporate in your incoming inspection, is be able to calculate number CP and number CPK. And I encourage our clients to calculate this number anytime you have a batch of parts coming in. So upper specification minus lower specification divided by 6 sigma. Now if you're normally distributed, this number is going to be 0. Because we have seen the spread is plus minus 3 sigma, which is 6 sigma. So when your process is normally distributed, then upper specification is going to be 3 sigma. Then this is going to be 3 sigma. It's going to come out to be 0. Okay. CPK value, it has got two values: mean minus lower specification, and upper specification minus the mean. Now these numbers will come out to be -1 and +1. So if I assume this to be 0, my mu to be 0, I can normalize my normalization. Okay. In Canada, and he always admires how quickly Indians adapt to new conditions, and they take everything in the stride. And so he also has some Indian clients. He always gives me great examples. And he says it's amazing that you have a certain change of circumstances, and Indian people adapt to that quite quickly. And And when I came here, I made a good effort to be a good Indian, that I can take everything in stride and not get rattled with glitches. So it's part of the game, I guess, in India, is to take everything in stride. All right, so we have we back up. So that's one way to evaluate your normal distribution. And then this is where I want to introduce a concept. And this is the concept which I think is important for if you have number of variables, you can line them up vertically and horizontally. Right now, I want you to think about correlation between these variables. Now, I'm not talking about the actual correlation such as defined by Newton's laws, or defined by Joule's laws, or defined by V is equal to IR. These are statistical correlations. Statistical correlation means that you really don't know how they are correlated except through collection of data. And when you correlate, when you're able to, the process is called, the concept is called process stack up. What does that mean is, on a simple scale, if I begin to get parts which begin to, let's say, my normal distribution is shifted, and I don't know about it. So my mu is supposed to be here. If I take a second subsystem, my mu may be also shifted,